Hello everyone, and today we are going to move to chapter 8 and continue talking about linear transformations. In sections 1.8 and 1.9 we were talking about matrix transformations. Now we are going to discuss a little bit more general linear transformations. So we are going to start with definition. Definition: a mapping from vector space V to a vector space W, which is labeled like T from V to W, is called a linear transformation if it satisfies two conditions. The first condition is homogeneity. If you multiply a vector by some scalar k and take a transformation from that resulting vector, you can also do just kind of transformation of vector u and multiply it by k, which means that you can take the scalar outside of the transformation. Second property is additivity. Additivity means that if you have two vectors and you add them in vector space V and then find the image of that sum in vector space W, it's going to be equal to separately sum of images of each vector. So all these vectors, this and this, belong to vector space W, the codomain, right? But the sum is going to be equal to the actually sum of images. So image of the sum is equal to sum of images, okay? If vector space V equals to vector space W, means that like you are doing mapping from space onto itself, then linear transformation is called a linear operator on V. And we're going to start right away with some rules for linear transformations. Theorem number one. Theorem number one: if T is a linear transformation from V to W, linear transformation, then there are going to be three statements about that. Linear transformation of zero vector is going to be a zero vector. This zero vector belongs to vector space V, and this one belongs to W. B. Linear transformation of a difference is going to be a difference of linear transformations. And C. Linear transformation of negative U is going to be negative linear transformation of U. I'm not going to prove all of them, but I'm going to concentrate on A and B. So for A, linear transformation of 0 can be represented as 0 multiplied by some vector u, right? Because 0 vector is can be like vector u multiplied by scalar 0. According to homogeneity rule, we can take the 0 outside, and we are going to have this vector, which belongs to space W, right, multiplied by 0, which is supposed to be equal to 0 also, just because of the same rule, right? We remember that somewhere in parentheses, that 0 multiplied by any vector is equal to 0 vector. That's like for V and for W, for both it's true. So that was for A. B. Transformation of U minus V can be represented as transformation of U plus minus V, right? And further, it can be represented as transformation of U plus negative 1 multiplied by V. Remember when we were doing vector spaces, we proved actually that like minus or negative V or minus 1 can be kind of represented. Now what we are going to do, use additivity. So it's transformation of U plus transformation of minus 1 V, and then use homogeneity on this term, and we are going to have transformation of U plus minus 1 transformation of V, right? And we remember that multiplication by minus 1 is going to be just like a minus. Okay, so that's T of U minus T of V. Okay, Let's now talk about matrix transformations, which we kind of had like from sections 1.8 to 1.9. So kind of that's going to be my first example. Example 1. Transformations which are using matrices. Are they actually going to be linear transformations? If you recall, for matrices, we had the properties which we have over here, like homogeneity and additivity. As a theorems, we actually proved them using the fact that how the transformation is constructed by using matrices. So basically, the idea of linear transformations, like more general, to use these two properties as a axioms or definition of linear transformation is coming from matrices where we actually prove them. So matrix transformations are linear transformations. Well, we just kind of proved them. Example number 2. Zero transformation. Zero transformation looks like this. Transformation from V to W, which is taking all vectors from V and transforms them into a zero vector. For vectors V belonging to vector space V. Is it linear transformation? Let's check. Let's check A and B to make like homogeneity and additivity. So A. Okay, let's check homogeneity property. That transformation of Ku actually equals to K transformation of U. Well, that's a homogeneity property, right? So what is transformation of Ku? Well, if you take any vector of space V, this transformation is turning it into zero. Just like because it works, like takes any vector from like space V, this one, and turns into zero, which belongs to W. Okay. What we are going to have on this side? Well, that's K, and transformation of any vector again turns it into zero vector. And if we multiply any number by that zero vector, we of course going to get zero vector again. So we do see zero from this one because that's a direct transformation of vector Ku, which goes to zero like directly by this statement. And like if we apply this K, Tu, we are going to get zero again. So, well, these two statements are true. Now, let's check B. B tells that Tu plus V must be equal T of U plus T of V. And let's check it. So, what is going to happen here? Well, this one is a vector of V. According to my definition, it's supposed to go to zero when I apply to transformation. So this is going to be zero. How about this? Well, this is going to be zero, the whole thing. And this is going to be zero, just because of the same rule. So what I have, I'm going to write it down like this. This, the left side zero, equals to right side zeros, which is like, of course, true. And let me erase this. So we just proved it. One more example, example 3, identity operator. What is identity operator? Identity operator transforms V space to V space, and identity operator of V is exactly equal to V. And we kind of familiar with this operator from matrix operators, right? Well, you probably can prove that homogeneity and additivity and B are working for identity operator too. I'm going to leave it for home. A plus B proof at home. Basically, guys, it's not going to be much proof. You're just going to check it. Okay, so what else do we need to know? Well, we're going to move to our next theorem. It's going to be theorem 2. Let T from space V to W be a linear transformation. If S, set S V1 Vn, which consists out of vectors V1 Vn, is a basis for vector space V, original vector space, then the image of any vector V, which belongs to original vector space V, can be represented as T of V, C1 T of V1, C2 T of V2, and Cn T of Vn, where C1, Cn are the coefficients from linear combination or kind of representation of vector V in a basis Vs in the space V. Well, that's a theorem, but actually there is not much to prove, right? So what we are trying to say in this theorem is that if you have a vector space V and you do have a vector V in it, which can be represented as a linear combination, we have a basis here, S is basis. We can represent any vector V as a linear combination of basis vectors, right? Because basis is a set of vectors which spans vector space. So like C1 V1 plus Cn Vn, right? If we apply a linear transformation to this vector V, according to properties of linearity, homogeneity and additivity, we can actually, instead of like applying transformation to the vector V, we can actually apply transformation to each basis vector and then multiply those vectors, the images of basis vectors, by the same coordinates or constants we were using over here. So, which is going to be nice because if we do have only one vector V, that's fine. But if we have many different vectors, we can build images of them using basis and the coordinates of the vectors in vector space V. They are probably not going to be the coordinates in the vector space W, but at least we are going to get those vectors. I'm going to show you an example of such transformation, and again, it's not necessary, maybe, that basis is going to become, after transformation, basis again, but at least homogeneity and additivity are going to provide us with resulting vector. Let's consider example of how we can use this theorem. Imagine that we have three vectors: v1, 1, 2, 0, v2, 1, 0, 0, and v3, which is going to be 1, 0, 1. And these three vectors are making basis for R3. How do we know this? Well, we obviously see that one of the vectors is a standard basis vector and two others are linearly independent, and kind of obvious that they are all linear independent. Now, let's consider transformation, which turns vector v1 into 1, 0, turns vector v2 into 2, 1, and turns vector v3 into 4, 5. Well, again, just some transformation. Now the question is, what is transformation of a vector 3, 2 minus 3, 5? What is going to be transformation? So what we are going to do, step number 1, find v, this is going to be my vector v, coordinates in basis S, which is going to be this, basis S. And second is going to be use them in image vector. Well, kind of. Let's do it. So I think we are going to, so this basis is not on orthonormal or like special basis, it's just a set of linearly independent vectors. And if you don't think so, you can just check the determinant of this like three rows and see that the determinant is not going to be equal to 0. So now we need to represent vector 2 minus 3 and 5 in like find the coordinates or as a linear combination of these vectors, right? So basically we are going to solve the system of equations, and I'm going to write down, sorry, I need to bring it down, 1 2 0 1 0 0 and 1 0 1. Need to multiply by C1, C2, C3. These are going to be the coordinates. And eventually we're supposed to get vector 2 minus 3, 5, right? I think I was supposed to actually write down them. Okay, let's start solving it. Well, it's not exactly row echelon form, but we probably can easily solve this just because like we do have like one leading variable here, one leading variable here. And if you exchange first and the second rows, you can kind of have one leading and eliminate like something here and have one leading variable here. I'm going to use back substitution. So I'm going to look at this last row and this column, and I'm going to see that 1 multiplied by C3 equals 5. So my C3 equals 5. And then what I'm going to see is that 2 multiplied by C1 equals minus 3. I'm going to use the second row and multiply it by this and see that it's going to be minus 3. From where C1 equals minus 3 over 2. And now I just need to find C2 by using last equation was 1, 1, 1, right? So I have minus 3 over 2 for C1 plus C2 and plus 5 equals 2. From where C2 equals 2 minus 5 plus 3 over 2. So I'm going to give me very nice answers. So I actually have minus 3 plus 3 over 2. Looks like I'm going to get minus 3 over 2. Yeah, let's double check too. Minus 3, 3 over 2. Yeah. So what my coordinates of vector v in basis S are going to be what? C1. What is my C1? Minus 3 over 2. C2 is, oh no. C1, C2 is also minus 3 over 2, and C3 is 5. Now, what I'm going to do, guys, I'm going to use the property that T of V is going to be C1 T of U1, V1, the basis vector, sorry, plus C2 T of V2 plus C3 T of V3. So C1 is minus 3 over 2. And where is my first image? First image is 1, 0. Minus 3 over 2, 2, 1. And the last one, sorry. Oh, I'm writing down the wrong place. Sorry. Wanted to write down over here. 3 over 2, 1. Hard to 1, 0. Minus 3 over 2, 2, 1. And plus 5, 4, 5. And let's just calculate what we have. 3 over 2, 3 over 2, 1 plus 2 and 20. So we have 20 minus 9 over 2. I'm trying to calculate my first coordinate. My second coordinate is 25 minus 3 over 2. I'm combining x components and y components here. Well, I'm not sure 100%, but 9 over 2, it's 4.5, so I have something like 15.5 here. And this one is 23.5, right? 25 minus 3 over 2. I think that's going to be my new vector. So that's going to be my image in my new space, W, which is two-dimensional space. Okay. Okay, guys, some more definitions. Another definition. If T is a linear transformation from space V to space W, then set of V vectors which belong to original vector space V, for which T of V equals 0, is called the kernel of T and denoted by curl of T. Let me visualize it a little bit. So that's space V, that's space W, and there is a transformation T, right? So there is a 0 vector here. All vectors from here which go into this 0 vector, maybe it's only one, maybe it's more, are called kernels. So kernel are vectors which belong to vector space V and can be one or more vectors which go right into 0 vector in W. Okay, good. Other definition. The set of all vectors W, let's say in W, vectors W, in space W that are images of at least one vector from V is called range of T, and I write it down, R of T. Visualization for range. V is W, and this is transformation T. Well, it can happen that you start using all these vectors and they do not take whole space W. They take some part. Maybe they take whole space, but maybe they take some part. This part, which has something in the back, which are images of some vectors from V, is called range of T. Okay, so let's consider matrix transformations as an example, like what is going to be like kernel and what is going to be range. So my first example number one, matrix transformation TA. Well, I don't know, from Rn to Rm. So what is going to be kernel? Well, kernel, the matrix transformation is what? TA of x is actually equal AX, right? Transformation. For kernel, we'll need to turn it into 0. So this vector belongs to Rn, original space. This one belongs to Rm, the final space. And that's what we have. All vectors which are turning into 0 are going to make kernel. Well, which vectors are turning into 0? Well, x solutions of homogeneous system, right? And we know this space of solutions as null space. So actually, kernel of TA is going to be what? Null space. Or space of solutions, right? What is going to be range? So I'm going to label it as 1, right? Range. Well, what happens to vectors x after we apply transformation AX? Well, they are going to become some vector b, and if x belongs to original space, this vector is supposed to belong to what? The final space or image space. If we just consider this part separately from idea of transformation, what are those vectors? These b's are vectors from this space which can be represented as a linear combination of vectors here, right? So imagine that we have a matrix A. Matrix A is looking like this, like A11, A1n, AM1, AMn. When we write down AX equals B, actually what we do, right? We write down A11, AM1 by x1, the first coordinate, plus second column plus plus, and the last column a1n and amn, right? It's supposed to be equal to this final vector, which is b. So that's vector b, which is b1 and bm. Well, what is this actually? Sorry, I put m here, supposed to be n. Sometimes I just kind of want to write down one thing and write down another thing. Okay, guys, what we have over here, that all vectors in vector space W are produced by linear combinations of these column vectors of matrix A. So, range, or all possible vectors of W, R of TA, is going to be what? Column space of A. Just because they are linear combinations of columns. And that's basically like whatever span of these vectors. Okay? Okay, more examples of range and kernel. So, sorry, example 2, zero transformation. Zero transformation. Well, zero transformation is taking all vectors from vector space V and transforming them into zero. So basically, kernel of such transformation is going to be all space V, because all V go to zero. I'm going to draw the picture. Space W, that's space V. So all vectors V go into one zero vector here. That's how transformation works. Oh, T0, I'm going to label it T0, okay? What is going to be a range? Well, the only vector which has image, which is image of something of V is 0. So range is going to be just one zero vector. And this 0 is from W. Okay? Okay. Example 3. Identity operator. So identity operator which is taking vector V and doing nothing with it. What is going to be kernel? Kernel are which kernel is going to be what? Which vector V is going to be like which vector we are going to, let me just set it, apply identity operator and get a zero vector. The only vector which is going to turn into zero, it's a zero vector, because like that's it, the zero itself. No other vectors are going to turn into zero. So kernel is going to be only zero vector. Okay, what is going to be range? Well, all vectors are going to have some, are going to be images of some other vectors which are going to be themselves, right? So range of identity operator is equal to all space V. Kernel is 0 and range is all space V. Something which is in the middle. Example 4. Orthogonal projection. Well, I don't know. Let's choose orthogonal projection on x-axis. Let's do vector v, and the projection is going to be this t of v, orthogonal projection. So guys, what is going to be kernel? Well, all vectors which are going to be projected into zero vector at this point. All vectors, well, what are going to be those vectors? Are going to be vectors which are going to be along y-axis, right? So kernel of this transformation is going to be what? A set of vectors with coordinates 0, y, right? Any vectors of this shape are going to turn eventually by projection into 0. What is going to be a range of T? Which vectors of new space, which is going to be along x-axis, are going to be images of some vectors from original space, like two-dimensional space? Well, all points on x-axis are going to make up image of some other vectors, which is like projection. That's going to be just projection, not only one vector, but many. So range is going to be all possible vectors along x-axis. We can label them like this, x0. But also, like, just because they are one-dimensional vectors, you just can label them with just x. Okay, let's continue. One more theorem. I think it's theorem 3 already. Probably. Guys, range and kernel by themselves are going to be subspaces. So if we have T transformation of V onto W, then A kernel of this transformation is a subspace of V. Range of transformation is a subspace of W. I'm going to do the proof only for A, okay? Not difficult to do for W. Remember that to prove that something is a subspace, we will need to check closure axioms. That if you, for example, if you do have two vectors, in like the set of kernel, the sum of them is also going to be in the kernel. Well, it's not difficult to check, right? Imagine that vector u belongs to kernel of T and vector v belongs to kernel of T. What does it mean? U belongs to kernel of T means that transformation of u equals to 0 and transformation of v equals to 0 because only vectors which transform into 0 are going to belong. Well, what is going to happen to the sum of them? U plus v. Is it still going to belong to kernel? Well, according to the linearity of additivity of transformation, we can write it down as T of u plus T of v, right? And T of u equals to 0, T of v equals to 0, so it equals to 0. So transformation of this sum vector is also 0. So u plus v also belongs to kernel of T. Second axiom was homogeneity axiom. This is additivity, homogeneity. Let's enumerate them better. So let's call it axiom 1, and next one is axiom 6, that Ku is going to belong actually to that subspace. If you multiply any scalar by your vector, the result is still belonging to that subspace. Well, let's check it. Transformation of Ku, it's K multiplied by transformation of U. If U belongs to kernel of T, that means that T of U equals to 0, which means that over here I have K multiplied by 0 from this. I'll substitute here. And that's going to give me 0. So actually this vector Ku belongs to kernel of T2. Just because it transforms into 0. Well, the space is closed. Closure axioms are working. Other axioms are going to work, we know. So it's going to be a subspace. Well, guys, you can check actually similar axioms, closure axioms for range. And the last definition we are going to have. We had so many definitions today. So, if we have linear transformation from V to W, linear transformation, then dimension of the kernel of T is called nullity. And dimension of the range of T is called rank. I don't know, nullity of T, maybe rank of T. You can put also rank of T and nullity. So basically, kernel itself, it's a subspace, but this subspace is supposed to have dimension. That dimension have a special name, nullity. Well, if you go back to matrix transformations, you probably are going to see why it's nullity, because, like, actually for matrix transformations, kernel is a null space, and dimension of null space is nullity. And also the range of transformation, well, since it's a column space, it's going to be, since it's a column space, it's going to be equal to rank. In this case, rank of A, but generally it's rank of transformation. And what is going to happen if you add nullity and rank? Remember, rank is number of leading variables, nullity is number of free variables. The sum of them is supposed to be equal number of variables. Number of variables here is equal to like n, how many variables we have, like, right? And that's matching dimension of original space, n variables. Well, for general spaces, we're just going to write it as a theorem. Theorem, which we're not going to prove that. Sorry, I'm going to nullity of transformation plus rank of transformation is going to be equal dimension of space V, original space. For us, for matrix transformations, it's dimension like n, because we are transforming Rn into Rm. Okay, that's all. So basically the formula is kind of keeping same from matrices. Okay, I'm going to finish at this point.